All right, let's try a different problem. This is a problem that I gave on an exam once upon a time. I changed one of the numbers because I liked where those numbers were better. So it says we're going to sketch the open loop response. I'm going to let you do that. Show a block diagram for the unity feedback control system. So if we're going to design a control system for this problem, what we need to do, here's a unit, here's what we can do. Here's G, here's K, here's the feedback loop. There we go, we're done. But we have to do a few things, like maybe we need to find out what the gain is and stuff like that. And so here's what we're going to do. So we're going to look at the open loop poles. Open loop poles is at S equals -1 and S equals -5. And then we're going to look at the real axis segments. We're going to look at sigma. So we know that the number of asymptotes is 2 plus or minus 90 degrees. The asymptote intercept point is -5 minus 1 divided by 2, which is going to be plus or minus 3. So it's right in the middle in this case. Sigma A equals -3. You can go ahead and do the breakout points if you want to, but I'm just going to tell you that's the root locus. And so then somebody says 0.707, so that's a 45-degree angle from here. A 45-degree angle from here, which is going to be about like this. Zeta equals 0.707. Theta equals 45 degrees. And so what that tells us is that where we want to have our desired root locations then are just about here. And so we say, okay, that's where we want our roots. That's the best place we can have our roots to be. So let's go ahead and draw these roots. This is going to be S plus 1. This is going to be the root S plus 5. How long are they? So we can use the magnitude criteria. We can use that K equals 1 over GH, and that means that we're going to look at this as being, so we got to put the 6 on the bottom, magnitude of S plus 1, magnitude of S plus 5, and all we have to do is find out how long they should be, each one of them. Oops, this is this long, and I'm going to put it over here, and I'm going to tell you that that's 3.5. This is this long. In this world, that's 3.5 too. So I'm just gonna, when you need it exact, go ask Dr. MATLAB. 3.5. So 3.5 squared over 6. 3.5. 2. K is equal to 2. And so if this is how we design it with our proportional gain only, we can look at what the transfer function for the proportional gain only is going to be numerator of G times the denominator of H. That's going to be S squared plus 6S plus 5 plus 6 KP. And so if we want to look at what the steady state gain for these things is, the steady state gain for this one is just going to be 6 kp over 5 plus 6 kp, and that's going to be 12 over 17. So we estimate that, and if we do a step response, we can see what that's going to be. So we can see we have some considerable amount of steady state error there. Maybe this is going to be too slow if we want to sketch the time response. Then what we want to look at here, this 1, 2, 3, 4, 4 over zeta omega n. Those are going to be the envelopes. We know that this is going to be 12 over 17, something like that. Here's the envelope. It's going to be 4 over zeta omega n, so this is going to be omega n is 17. Square root of 17, let's call that square root of 16 is 4. So 4 over, we know what zeta omega n is. Zeta omega n is 3 minus, so 4/3. So this is 4/3 of a second. So if we want to wait 1 1/3 second for this to settle in some way, do we want to wait that long? No, we can't wait that long. And so, in fact, somebody tells us, by the way, you can't wait that long. What you need to have is a settling time of 0.4 seconds. So the specifications say that Ts equals 4 over zeta omega n has to be equal to 0.4, and that tells me that zeta omega n has to be equal to 10. So here's zeta omega n is equal to 10 minus 10. That's zeta omega n is equal to minus 10. That tells me that that is where our desired root locations need to be. And so I'm going to draw those vectors in this particular case. Again, what the question would be is how do I bend my root locus so that this is s plus 0, s plus 1, s plus 5, and what we need to do is we need to add a 0. Where do we need to add a 0? Nobody ever really quite knows exactly where to add 0, so I'm going to try to find a different color here to add the 0 with. So what I'm going to do is I'm just going to say, let me say if I make my 0 here at 0 is at s equals minus a. I'm going to put my 0 right there. And then in that case, I can kind of just draw this vector here. And then I know that this is theta a. I know that this is theta s plus 1. And I know that this is theta s plus 5. Now I kind of have to get out my protractor a little bit. I'm just going to tell you what these numbers are. This is 132 degrees, and then this number here, theta s plus 5, is 115 degrees. But I don't know what theta a is, because I'm still trying to figure out where to put it to make that work out right. So what I can do is I'm going to use my angle criterion, which says the angle of KGH is equal to minus 180 plus or minus K360. So if the angle has to be 180, so the angle of KGH, so I'm going to use minus 180, is equal to minus the angle of S plus 1, minus the angle of S plus 5, plus the angle of S plus A. All right, the reason these are minus is because they're in the denominator, so that's a negative angle. So that's going to be minus 132 minus 115 is equal to minus 180 plus theta A, and that's going to tell me theta A has to be equal to 67 degrees. So one easy way to find theta A is equal to 67 degrees is just to realize that if this is theta A down here, then this is also theta A down here. And so what I need to do is I need to make an angle of theta A that is 67 degrees. It turns out I know about where that is, 16, 17. It's about minus 17. A equals minus 17. That's where the A goes, right there. You can go measure that with a protractor yourself, S plus A. There it is, S plus A. And then so now I know where my 0 has to go. I've just added a 0. And what that looks like in terms of my closed loop feedback, I still have a KP. What I'm going to do here is just add an S plus A. I don't know what that means exactly. I'm just going to put in G right here. And when I do that, I get this root locus. And I'm just going to, again, you kind of sketch these loci around a little bit. I'm looking for the right colors here. I'll use a purple one here. And essentially what that does is that forces the root locus to go right through this point. Putting that 0 there makes the root locus go right through that point. And isn't that nice that it does that? And so now what I'm going to do is figure out what the gain is. Kp is equal to 1 over gh, which is, in this case, is going to be the angle s plus 1, magnitude of s plus 1, magnitude of s plus 5, divided by 6 times the magnitude of s plus a. And again, you can do all the geometry if you want to do the geometry. That's okay. We're just doing it quick and dirty here. So I'm going to see how long is that. I'm going to call that 13. So s plus 1 is 13. I'm going to see how long this one is. I do that one right? Yeah, I did. I'm going to do this one again. Let's call that 11. And then I'm going to do this one. That's going to give me, call it 12. 11, 12. That tells me what my gain Kp needs to be here, right? 13 times 11 divided by 6 divided by 12, 2. I'm worried that I've made a mistake here, but oh well. So now we're going to look at what the closed loop transfer function for this system is. T of s is equal to the numerator of g Kp times s plus a. This is 17, right? Divided by s squared plus 6s plus 5 plus Kp times s plus 17. In this case, I'm going to rewrite this denominator here. This is s squared plus 8s, because that's a 6s plus 2s, plus 5 plus 17 Kp. Up here, this is going to be Kps plus Kp times 17. And in this case, what we get is our steady state gain, T of s equals 0, is going to equal to 17 Kp over 5 plus 17 Kp, which is going to be Kp is 2, 17 times 2 divided by 5 plus 17 times 2. 0.87. Huh. So that improved our steady state gain some. Some people might say, why don't we just make the gain go higher? What happens if we make the gain go higher? What happens here? When we make the gain go higher, guess what happens? Goes here, goes here. So all we do is really improve our performance with a higher and higher gain and reduce the steady state gain. Okay.